Okay, thank you for clicking on my talk. My name is McCullen. I'm a researcher at the Blue Marble Space Institute. My background's in cosmology, but over the last few years, I've grown more and more interested in habitability, precisely because I believe that it can inform studies on the multiverse. So the multiverse has been notoriously difficult to test, but what I hope to convince you of is that by marrying these two fields, we're able to use the multiverse hypothesis to generate a host of predictions for what life needs that can then be tested by observation. I probably don't need to go into too much detail for this crowd, but briefly, the multiverse hypothesis is that other universes exist and have different laws of physics, by which I mean values of the constants, so things like particle masses, strengths of forces, etc. This has historically proven difficult to test because, in all probability, we're confined to our universe and don't have any real hope in observing other universes directly. Um, Nevertheless, I'll show that there is a path forward by generating predictions that can indirectly give indication of the existence of these other universes. So in the multiverse context, we can't explain the values of our constants from fundamental principles, but instead what we can do is develop probability distributions for observing any particular value of any constant. And there's this notion that goes by the name of the principle of mediocrity, which is that we should expect to be typical observers in the sense that the probability of our observation should not be too small. So mathematically, this is operationalized through this formula where the probability of observing any constant x, given that we are observers, is proportional first to the fraction of universes that have that particular value of the constant, but then is weighted by the total number of observers produced by that particular universe. And so this first factor is relatively straightforward to compute from generic physical principles that doesn't depend too much on the UV completion of physics. But it's the second factor that is proven the most difficult for cosmologists. The state of the art for estimating the number of observers is usually something as crude as just the fraction of baryons that fall into large enough galaxies. But my claim today is that this crudeness is the source of the dearth of predictions of the multiverse, and that if we're able and willing to do a more honest job estimating the number of observers per universe, then we are able to generate a whole host of predictions that can then be tested. Cosmologists, as a rule, are usually not very well equipped to estimate the number of observers per universe in any great detail. But there is a whole community of people who study the conditions necessary for life and complex life. These are astrobiologists, so we can collaborate with them. The issue becomes then that if you ask any two astrobiologists what life needs, you will get two different answers. So, for example, does life need to be on an Earth-like planet? Does it need to be carbon-based? Does it need to be water-based? Can it exist on icy moons? Does it need to be around a sun-like star? Can life exist around binary star systems? Can it exist on tidally locked planets? And on and on and on. So for each of these habitability conditions, there is no consensus on whether they're right or wrong, which makes the calculation for the number of observers highly dependent on the assumptions we make. I'll argue that that's precisely the position we would like to be in because we don't need to commit to a single theory of habitability to compute this value. But what we can do is just run through all of them, and in fact, all combinations of all different habitability conditions, and determine which are compatible with the multiverse in the sense that they make our observations typical and which are not. Okay? And when we do this, we end up with, so far, a list of over a dozen predictions for which habitability conditions are true. And while we don't know which are true at the moment, there are plans in the future to go out and search for other examples of life. And as long as we're not literally the only ones in the cosmos, eventually we will have a statistically significant sample of life. And at that point, we can try to determine what the presence of life correlates with, which conditions, and whether these conditions are in line with the predictions that we've made through the multiverse hypothesis. So I have this flow chart which summarizes the logic a bit more succinctly. The logic is essentially in the multiverse context, we have to ask why we're in this particular universe. And the answer is that this universe is good at making life. And while we don't know what life needs, it's more manageable to address what our universe is good at. So for each habitability condition H, such as the ones I rattled off a minute ago, we ask, is our universe good at it? If yes, then life should depend on that habitability condition. If no, life should not. And then we can go out and test with future observations whether life depends on that habitability condition. If the observations are consistent with the predictions, that is evidence for the multiverse. And if not, that can be, in some cases, quite strong evidence against the multiverse. So a bit more graphically, here I have two different habitability conditions, A and B, on the left and right. And I have for each a two-dimensional slice of parameter space for two constants, which I'll describe in a few slides. And we can see that, so for this, the contours denote the population of observers under that habitability assumption. The star here is our universe's values for these two constants. And we can see that for habitability condition A, our universe is quite far from the centroid of this distribution, whereas for condition B, we're quite close to the top of this distribution. So in this way, we can say that habitability condition B is consistent with the multiverse in the sense that our observations are typical, and habitability condition A is not. So we expect B to be true and A to be false. And we can even quantify this in terms of probabilities. And I'll explain a bit more about what these two habitability conditions are in the next few slides. I just wanted to illustrate the abstract logic that we're employing. So the strategy is to just accumulate as many habitability conditions as we can and run them through that logic pipeline. It is quite an involved thing to do an end-to-end estimate of the number of observers. You have to take many different things into account, all the way from chemical abundances, planetary physics, stellar physics, atmospheric properties, origin of life scenarios. So this has taken a few years now and has resulted in 9 going on 10 papers with the following collaborators from a variety of fields. So I'm clearly not going to have time to talk about everything that we've done, but what I hope to do is to step through a few examples of what I think are some of the most interesting predictions that we've been able to generate, just in order to illustrate the basic logic and this methodology as a principle for generating predictions. So first, a bit about how we go about estimating the number of observers per universe. We phrase it in terms of this Drake-like equation, where the number of observers is proportional to the number of stars in a universe times the fraction of stars that possess planets, the average number of planets in those systems, the probability that a planet possesses life, the probability that biosphere will develop intelligence, and then optionally the number of observers per biosphere. And all of these quantities will be functions of the fundamental constants. We ordinarily will group these last 3 into what I call the habitability of a planet, H. And for the purposes of this talk, I'll focus on mostly these 3 variables. Alpha, the fine structure constant, which parameterizes electromagnetism, beta, which is the electron to proton mass ratio, and gamma, which is the strength of gravity, or the proton mass over the Planck mass. Other variables that we include in our analysis are the up and down quark masses, the galactic density, and a lambda, which are not shown here. And for each of these, we compute the probability of our observations, which is given by this cumulative distribution function for all of these constants, probability of observing a value at least as small as ours. Sometimes this is augmented by other observables, such as the probability of being around a sun-like star. And I'll frequently refer to this naive Bayes factor, which is the product of all of these probabilities in order to succinctly compare different habitability conditions. All right, so for starters, the first factor, the number of stars in a universe, firstly depends on the number of protons in a patch of the universe, which I won't talk about during this talk. But secondly, it depends on the number of protons in an average star. So one contribution to this factor is just the size of stars. The average star mass is given as a small multiple of the minimum stellar mass, which can be expressed in terms of constants like this. And this induces a contribution to the probability that will be present for any habitability condition that we consider, just based off the number of stars in the universe, which in terms of constants is this. So that you can see that this favors large values of gamma, the strength of gravity, which is, if you plot just this value, ignoring all other contributions to that Drake-style equation, you get that the distribution of observers as it tracks the total number of stars to highly favor these large regions of large gamma. And so for this bare bones theory of habitability that treats every star as equally habitable, we end up with a very low value of observing our strength of gravity. So from this, we conclude that this cannot possibly be a viable theory of habitability, which should probably come as no surprise. But the first theory or prediction that we get from this logic is that life should depend on stellar properties in some way. And the more sophistication we add into this machinery, the more sophisticated our predictions will be. So next off, we can try to estimate or find some ansatz for the habitability of a planet. And one thing that you could guess is that the habitability of a planet is proportional to its lifetime, which should closely track the stellar lifetime, which can be expressed in terms of constants in this way. Here, introduced this variable lambda, which is a dimensionless way of parameterizing stellar mass. If we do this, this would favor universes where stars live for longer. And you can see that this habitability condition pretty drastically shifts the distribution of observers throughout the multiverse. But it increases our value of observing our strength of gravity by a few orders of magnitude, but it still falls short of what I would say is typical, because this is still quite a small number. So the conclusion from this is that this is not a viable theory of habitability, because it would imply that there are universes out there where every star lives for trillions of years, and we would expect the vast majority of observers to be in universes like that, and we would represent a minority living in a universe such as this. So the prediction from here is that we should not expect to find a strong correlation between the presence of life and stellar age. On the other hand, here I'm displaying a habitability theory that actually is compatible with the multiverse. and that is that the habitability of a planet is proportional to the total entropy or the total disequilibrium that a planet experiences. So there's good evidence that this sets the size of the biosphere. I've cited the paper here, but I've also shown a kind of back of the envelope calculation that the size of the biosphere is a couple orders of magnitude shy of the total number of bits per second that is incident upon our planet. This habitability condition requires photosynthesis, so it turns starlight into chemical energy. There's arguments in the literature that this is necessary for animal life simply because it produces oxygen, which is necessary for aerobic metabolism. The interesting thing to note is that this is not necessarily guaranteed in a multiverse context, but is reliant on this coincidence that the spectral temperature of starlight is about equal to the atomic binding energy, which even 40 years ago was realized that can be expressed in terms of the constants by this near equivalence. So this provides some soft restriction on the values within parameter space where life can exist. In terms of our theory of habitability, we say that it's proportional to the total entropy, which can be given in terms of planet area, orbital radius, luminosity, and so on in terms of the constants as such. And if you look at these maps of the multiverse, then our universe is quite close to the center of these distributions. And in terms of probabilities, they're all quite typical. So the prediction here is that it's at least consistent to say that habitability should closely track entropy, and so we should expect life to be more prevalent on planets with a higher amount of total entropy produced. So that was kind of some very simple ansatz for what habitability should look like, but we can layer it with more and more complexity. Here, I want to point out one thing that I think is pretty underappreciated in the literature, which is that isotope stability plays a very strong role in the features of these other universes. So I think everyone probably has heard about the story about carbon and oxygen abundances with the triple alpha resonances, but the same holds true for all the other elements as well. So to a first approximation, you can think of stars as producing a profile of nuclei with fixed nuclei numbers, kind of independent of what the stable configuration is. And then after those nuclei are produced, they decay through beta chains to whatever is the most stable amount of protons and neutrons for that nucleon number. But that nucleon number for every given nuclei is relatively fixed. And what the stable isotope is can be summarized by this semi-empirical mass formula, which can be written in terms of the constants. And we find that there are large shifts if you change the values of either the quark electron masses or the strength of electromagnetism. So, for example, if you increase alpha by just 3 or 4%, nitrogen 14 becomes unstable and will decay into carbon 14. So in universes like this, as I've shown in a single dimension in this plot, once you cross this threshold, so the black line is our universe, but if you increase alpha by a little bit, these universes are much depleted in nitrogen by a factor of a few hundred. And so our atmosphere is predominantly nitrogen. If you think that that's important for life, then these universes will be much less habitable. The closest boundary is actually less than 1% away, in which case sulfur becomes unstable and decays into phosphorus. These are both important elements for life, but phosphorus is usually a limiting element in terms of ecosystems. So in universes like this, if phosphorus is 50 times greater, you can even make the case that these universes would be even more habitable than ours. And here I have displayed a two-dimensional version of that plot in terms of alpha and this most salient feature of the quark and electron masses, where you can kind of see this checkerboard pattern across parameter space. So the strongest assumption would be that only the rhombus that we inhabit is habitable. I think the strongest assumption in the opposite direction is that any of these are habitable and quite independent of the actual element abundances. But I think more realistically is that some of these regions of parameter space are habitable and some are not. And it will take a bit more work to kind of determine what the actual effects would be for any given change of the abundances, which can be, as you see, very large. Another habitability condition that's talked about quite often is that the presence of a large moon may be necessary for complex life. So on Earth, it stabilizes our tilt over geological timescales. The interesting fact about this is that our universe is somewhat exceptional in that a bare terrestrial planet with no moon would have unstable tilt. It's a consequence of the fact that the obliquity drift timescale is roughly coincident with one of the solar system resonance timescales, which is set by the parameters of some of the outer gas giant planets, such as Jupiter. So Earth just happens to lie in this danger zone when on its own. But when presence of a moon is added, it kicks it out of this danger zone, making the obliquity stable. So all these values can be computed in terms of fundamental constants, but what we end up seeing is that the scenario we observe where a bare planet would be unstable, but a planet with a moon becomes stable is quite rare in the multiverse context. In our universe, large moons around terrestrial planets are the exception rather than the rule, and that holds even more so within the multiverse. So this idea of habitability doesn't really make much sense in the multiverse context. The prediction being then that we should go out and look for life, and if it requires the presence of a large moon, then we would be unable to explain why we're in this universe as opposed to others. We can go on. Water abundance is another crucial feature for habitability by anyone's account. The interesting thing about this is that Earth's water content is precisely the amount to kind of half cover the surface. So by weight, it's about 2 × 10⁻⁴, which is a bit of a precarious scenario, especially given the fact that we don't actually know the source of Earth's water at the moment. There are multiple schools of thought about this. It either came from asteroids or comets or the interaction of an oxidized magma ocean with an initial hydrogen atmosphere. And to explain this kind of coincidence, many people rely on the weak anthropic principle, which restricts its attention to within our universe. But there have been a number of forms proposed for how habitability depends on surface water fraction, which have been given in the literature. And what we can do in the multiverse context is compute the amount of water for a terrestrial planet for any of these scenarios and compare that with the list of habitability conditions that have been proposed in the literature. And we see that in the multiverse context, not every scenario is compatible with every habitability ansatz. So this again provides some predictions for which combinations of sources of water and habitability forms are compatible with the universe or the multiverse. All right, we can think about origin of life scenarios. So the general ansatz here will be that the probability of life developing on a planet is proportional to the amount of disequilibrium produced by whatever origin of life scenario we think is important. Here we considered 10 different ones and found expressions for the total amount of entropy produced as a function of these constants. Um, and at this stage, what we can do is compare each of these theories and kind of cross correlate those with other theories of habitability that we've come up with in our previous papers. And we can see that certain of these are always incompatible with multiverse hypothesis. So these two are solar energetic protons and XUV flux, which could be important for the creation of prebiotic molecules on early Earth. The two different flavors of panspermia seem to be incompatible with the multiverse just because there would be universes where panspermia would be much more prevalent. For the remainder, we see that these origin of life scenarios can be compatible with the multiverse, but only for specific combinations with the other habitability conditions that we found. So this provides further predictions for what the origin of life scenario should be within the multiverse context. And then lastly, in the previous slides, I've restricted my attention to human-like observers on temperate terrestrial, like Earth-like planets. But that is unnecessarily restrictive. And in fact, if we consider more exotic environments, then we can then place even stronger constraints on the relative habitability of these environments. So here's a cartoonish picture of one dimension of the multiverse. And so previously we were restricting our attention to this question, which is the probability that we find ourselves in a universe such as this, given that we're human-like, which would be given in terms of this blue curve over the blue plus green curve. But if we consider an additional population of observers that are not human-like in whichever dimension we choose to consider, so say if they live on tidally locked planets as opposed to our Earth-like tidally unlocked planet, we can then consider this expanded probability, which is the probability of being in our universe and human-like, which includes this additional term encapsulating the number of exotic locations throughout the universe, weighted by this relative probability R, and demanding that this probability be reasonable, let's say greater than 0.05, allows us to place restrictions on what the relative habitability of these different locales is. And this logic can be used within our universe, which is done in this column. But quite often, if we employ this logic in the multiverse context, we get even stronger bounds. So for example, for rogue planets, these are planets that have been ejected from their solar system. We find that just based off pure numbers alone, they should probably be less habitable than bound planets such as Earth, which is probably not surprising. But the constraints are fairly weak. If you use this in the multiverse context, you get very strong bounds for how habitable these planets can be. And same with water worlds. Okay, so that's it. I hope that this whirlwind tour has at least convinced you that it is possible to use the multiverse framework to make predictions about the nature of habitability within our universe. Here I have a histogram of a bunch of different habitability conditions, and you can see that for the vast majority of them, the probability of our observations is extremely, extremely low, and it's really only a very small minority of habitability conditions that are consistent with the multiverse hypothesis. I've generated a lot of independent predictions for habitability, and the situation is that if the multiverse is true, we expect all of these predictions to be true and verified by observations eventually. If just a single one is found to be wrong, that could constitute in some cases, extremely strong evidence against the multiverse hypothesis. So in this way, even though in all likelihood, we will never be able to directly observe other universes, we can still infer their presence through these indirect effects. So thank you all for your time, and I'll be available for questions throughout the conference. Thank you.